Okay, hello, welcome to this week's recitation. So let's get started with the first question, 4.2.3. So the question, we have the siphon spillway set up like this, and we want to transfer the water from here to the downstream area here. And from the problem, it tells us that if the pressure is less than minus 9.8 pound per square inch, then we will have the cavitation problem. So the question asks that whether this engineering design will have the cavitation problem. So that's the problem that we want to solve. And the spillway that we have here have the cross section equal to 12 feet square. And other setup is like this. Okay, so by just looking at this setup, we can know that the pressure at the highest point should be the lowest. So if we want to see whether this engineering design has a cavitation issue, we need to know the pressure at this point. If this point has the pressure higher than this value, then it's safe from the cavitation. But if it's lower than this value, then we have that issue of cavitation. Okay, so in order to solve the pressure at this point, we will need to use the energy equation. But as we know, energy equation have the height, pressure, and the velocity term. But at this point, we only know the height at this summit. And we don't know the velocity, neither the pressure. So what else can we use to figure one of these unknowns so we can actually solve the pressure term at this summit point? We can first use this entrance and exit to use the energy equation to solve for velocity. Then we use that velocity to solve the pressure at this point. Okay, so let's start. The goal is that we want to find the velocity and the pressure at the summit point. So this is S, PS. Okay, but we cannot solve two unknown with one equation. So let's solve the velocity first, because the velocity is equaling this spillway. So let's use this A point and this B point to solve for this VS. So write down the equation, write down the energy equation. So we have HA plus PA divided by specific weight plus the velocity term 2G equal to HB plus PB divided by specific weight plus the velocity term 2G plus the head loss. Okay, so we know that the velocity at this entrance and exit equal to 0 because this water body, there's no velocity. Might have a velocity, but it's small enough to be ignored, so these two terms can be cancelled out. What else can we simplify this equation? This term is also equal to 0 because PN and PB are 0. Then we know HA, which is 52 here. So this is 52 feet. HB HB is 0 because we select the HB as the dead end. So we know the value for this head loss. So 52 equal to the head loss, which equal to the friction loss plus other minor turn minor head loss. Okay, and here we consider the minor head loss of the entrance and the exit, which is, and also the friction term is 2.5 times the velocity term, which is provided by the problem itself. So we can further write down this equation to 2.5. This is the friction loss, and the entrance coefficient is 0.5. This is KE plus the excess coefficient, which is equal to 1. This is KD times the velocity term. Okay. So from this equation, and we know G is equal to 32.2. Okay, so you plug the G into this equation, and then the only unknown is this V. So you can use your calculator and you will magically find this value for V. So we just write down the value for V, which is equal to, actually, we don't need to calculate all these terms because we need this entire velocity term. So instead of calculate the velocity directly, we calculate this term, the value for this term. So this term will equal to just divide 52 divided by this summation. Okay, you will get this term, velocity term, is equal to 13 feet. Okay, that's our first step. And this V is actually V8 because the velocity inside this spillway is equal. It will not change. The area is not changing, so the velocity will remain the same. And next step, we can solve for the pressure at this summit because we already know the velocity term. This pressure is the only unknown that we don't know. So now, let me change to a different color. We use this A point and this summit point and use the energy equation to solve it. Okay, so let me just squeeze it down here. HA plus PA divided by, okay, let me just quickly write down this, equal to HS plus PS plus VS 2G plus the head loss. Okay, similar to the previous one, we can cancel out this because PA and VA are equal to 0. Okay, and we know HA is equal to 52. This is equal to 52. And HAs is equal to 60, right? And VS, this term, so this is the term that we want to solve. And for the velocity term, we already know that the velocity term is equal to 13 feet. So this is 13 feet. And that's calculated for the head loss, okay? Head loss, oh, sorry. The head loss here is similarly equal to the friction loss plus the minor head loss, summation k times the velocity term. Okay, and here we only have the entrance head loss, and the entrance head loss is equal to 0.5. So we can this term is 0.5. How about the friction head loss? The friction head loss that the problem tells us is equal to this part, but now we only consider the first segment of the spillway, which is the distance ratio between this segment and this segment are equal to 1 to 4. Okay, so the friction head loss for this part is only 1/5. So this is 1/5 times 2.5 velocity term. Okay. Okay, let's just organize this, and we will got 1/5 times 2.5 is 0.5 plus 0.5 times the velocity term. Okay, and we can plug that into we'll plug this head loss into here, and let's organize this again. Let me squeeze it to here. Okay, so 52 minus 60, we have minus 8 will equal to 0.5 plus 0.5 is equal to 1, and we have another velocity term here, so it's actually 2 times the velocity term, and this term is equal to 13, which we have right down at here. Okay, and we plus the unknown that we want to solve, the pressure term. Okay, now you have this final equation, then you just plug the number in, and you can easily solve for this unknown, which is equal to minus 34 feet. Okay, and we simply do the unit conversion, then we know that P is equal to minus 34 times 62.3. This is pound per cubic feet, and then we divide this into 144 inch square, and this will have the final answer 14.7 pound per square inch. Okay, so we solve the pressure term for this submit point, and whether this will trigger the cavitation, the answer is yes, because minus 14.7 is less than the critical pressure, which is minus 9.2 pound per inch square. So yes, we will have a cavitation issue for this engineering design. Okay. Okay, so let's look at the problem for 4.2.7. Similarly, we want to examine whether this, we want to examine the cavitation issue. And the question tells us we want to pump the water from the aquifer to the water treatment plant, and we want to place a pump at some place in this pipe, and we want to solve what is the maximum height that we can place this pump that will not cause this cavitation issue. And here we have the information that provided from by the problem itself here. So similarly, we solve it by the energy equation. So let's pick the 2 points that say this is point A, and we want to place the pump somewhere in this pipe. Let's say this point is A, which is the location where we place the pump. So let's write down the energy balance equation. H A plus PA plus the velocity term will equal to the location of the pump and the pressure term for the pump plus the velocity term plus the head loss. Okay, so as we do this many times, let's try to simplify this, because we can choose these A points as our datum, which means this term, this term will equal to 0, right? And PA, because the A point is already outside of a pipe, so this PA term is also equal to 0. And there is no velocity in this aquifer, so the velocity term is also equal to 0. Okay, and we already the problem already told us minus 32 and minus 23 feet is the criteria for the cavitation to happen. So this, and we want to calculate the maximum height. Therefore, this term we will use 23 feet. So what else that we don't know? The velocity term. Okay, the velocity term, we can also solve it by the desired flow rate that we want to pump through this pipe. And we know that the flow rate is equal to the area times the velocity. So we can solve the velocity by flow rate divided by area. And we already know that this pipe has a diameter equal to 24 inch, which is equal to 2 feet, and it's a circular pipe. So the area, the flow rate is 50 CFS cubic feet per second, divided by the area, which is 2 square, the radius square times pi. So we know the velocity will equal to 15.9 feet per second. Okay, so we know this term. This V is equal to 15.9. What about the head loss? Okay, let's calculate the head loss. Let me change to a different color. Head loss is equal to the friction loss plus the minor head loss. Okay, and the problem tells us we can ignore the friction head loss. So this term will equal to 0. And we have the entrance screen here, which have the coefficient equal to 2.5. So the end result for this head loss is 2.5 times the velocity term. Okay. So it seems like we know all of the information, and the only unknown in this energy equation is this height, which is the information that we try to solve for this problem. Okay, so let me reorganize this equation down here. So 0 equal to HS minus 23 plus the velocity term 1, this one, and the head loss plus 2.5, this one, times the velocity term v2 to g. Okay, so basically you just need to plug the value into here. G is equal to 32.2, v is equal to 115.9. So plug the value inside this equation, then you can solve HS is equal to 9.26 feet. Okay. So this distance will be 9 feet. Okay, now let's look at the problem 4.2.9. So it's really similar to the previous one, but this time we switch the system setup to 2 reservoir. So we have the pump here, and we want to find a place to install this pump to pump the water from reservoir A to reservoir B. And the question asks us what is the maximum distance from this reservoir A that we can place this pump without any cavitation problem. So I guess you already know how to solve this based on the problem that we solved previously. But let's still write out the balancing equation. So let's choose 2.2 have the to use the balancing equation to solve the pressure. To solve the distance L here. Okay. So let's choose A and these S points to use the energy equation. Okay, let me write down the energy equation here. Plus VA squared to 2G equal to H's plus P's. Okay, so this is the energy balance equation. What is the next step? To simplify it, right? So how can we simplify it? We know HA, which is equal to, if we choose the data at this line, so the HA, we use the surface height here, which is equal to 4 meters. So this term is equal to 4 meters. How about pressure term? This is a reservoir and it's an open surface, so we can simply say that PA equal to 0. And similarly, the VA, because this is reservoir, is much larger than the pipe, so the velocity is also equal to 0. What about HS? HS is equal to 0, right? Because we choose this line as our data. So this is 0. And the problem itself also provides us the criteria for the cavitation to happen, which is that's the pressure term. When the pressure term is less than -7 meter, then the cavitation happens. So to find the maximum distance at this for this L, we use the maximum value for this pressure term, which this means this term is equal to -7. Okay. Now the velocity term. We cannot simplify that, right? Because it's already in the pipe, and in the pipe, if we want to pump the water, it should have the velocity. So as we do that a lot of time, this engineering design is designed to transfer the water at the flow rate equal to 4.5 cubic meter per second. And it also tells us the diameter of the pipe, which is 80 centimeters, equal to 0.8 meter. So we can calculate the area, and if we know the area and the flow rates, then we can calculate the velocity. So let's do that. Flow rate equal to the area times the velocity. So the velocity is equal to the flow rate divided by the area, and flow rate is equal to 4.5 cubic meter per second divided by the area, and this is a circular pipe. So the area is the square of the radius times pi. And if you use your calculator to calculate this term, it will equal to 8.95 meter per second. Okay, so now we know this velocity term because we know the velocity, and v, the velocity at this pump location is equal to any location in this pipe because the area is not changing, so the velocity also remains constant. And the last term is the head loss. How can we calculate the head loss? So let me use different color here. Head loss is equal to the friction loss plus the minor head loss. Okay, and if you remember the equation, which you should, because most of the questions need this equation, the friction head loss is equal to the factor A times L divided by the distance divided by the diameter times the velocity term. Okay, so we know the L is the parameter that we try to solve because we want to find what is the maximum distance to place this pump. So this L is the term that we want to solve, so remain there. And we know the diameter is equal to 0.8 meter here. Okay, and we already know the velocity term, so the only unknown in this equation is this factor F. How do we solve this factor F? So from last homework, you already know if you want to find out this factor F, you need to use Moody Diagram. Okay, so Moody Diagram, in order to solve this, you will use the Moody Diagram, right? And the Moody Diagram needs two items to find out this factor. The first one is this number. The second one is the Reynolds number. So because this is a rough concrete pipe, so we have this E, relative roughness, equal to, let me see, 0.6 millimeter. And we have the diameter 80 centimeter, which is equal to 800 millimeter. So that means we have this value equal to 0.00075, okay? And the random number equal to dV divided by the dynamic viscosity. And you should also remember this equation because we use this so many times that you should remember. Okay, so the diameter of the pipe is 0.8. Velocity is 8.95 divided by the viscosity of water, which is 1 times 10 to the power 6. Okay, then if you plug these, if you use these two numbers and the Moody diagram, then you can find out the factor of F is 0.0185. Okay, this is too ugly. 185. Okay. So now we know HF. So what about the minor term? The minor head loss here, we only have the entrance minor head loss, and the coefficient for the entrance is equal to 0.5, as we use this value in previous problems as well. So we know this summation k is simply equal to 0.5. So now you know this HF, you use this equation, and the only unknown is L. Velocity you know, G you also know, this G is equal to 9.81. F you already used the Moody diagram to find out, so you also know that. Okay, and yeah, the velocity here you already know is equal to 8.95. So let's reorganize this Halo's equation. We will got let me see. Zero 0.0185 LO divided by 0.8 plus 0.5 times the velocity term. Okay. So next, you just need to plug. Let me change different color. You plug this Halo's term to here, and the only unknown is L. You know all this information, right? And you know that this velocity now is equal to 8.95. G is equal to 9.81. So you can just simply use this equation, use your calculator, plug in all this number, and you can solve this L. And here I just tell you the answer is equal to 51.6 meters. Okay, so we have solved this problem. Do a quick review. So now you have the two reservoirs, and you use a pump to pump the water from reservoir A to reservoir B. How do you solve the maximum distance from this L to place this pump without any cavitation issue? And here we use the energy balance equations at this A point and this S point, which is the location where we place the pump. And you just simply plug all the information here, and you use the flow rate to calculate the velocity. Then you use this velocity to further calculate the halos. And in these halos, we consider the friction loss and the minor halos. And for the friction loss parts, you need to use the Moody diagram to solve this F factor. And because of this friction loss, we have this L parameter that we want to solve. Okay. So after that, you know the minor halos, the entrance halos, and you also know the friction halos in terms of this L parameter. Then you plug this value back to this balance equation, and the L will be your only unknown in this equation. Then you can solve that error. Okay. Okay, now let's look at the problem 4.2.12. The problem have the setup look like this. It seems like really complicated problem, but actually it's not. So that's first thing what the problem asks us to do. We want to determine the minimum pressure node that will ensure the pressure inside this pipeline remain positive. Okay, that is the thing we want to solve. So we need to first guess at which point that we will have the lowest pressure. If we can know that, then we can just calculate to ensure, okay, that point have the positive value, then we can solve what is the minimum P node to ensure that points have a positive pressure, right? So usually the highest points have the lowest pressure. And in this pipeline here, we have 2 points that have the same height, which is these points and these points. So now the question becomes which points that we should choose to do the calculation. And because in this problem, we also consider the friction loss. That means these points, if the flow is from this A reservoir to this B reservoir, so we have a flow direction that this way. So if we choose these points have the further lower height because we have the we consider the head loss during this section here. Okay, so this is the points that we want to use to solve P naught, and I write down this point as C. Okay. Now, as we have done this in previous problem, the first thing we need to do is that, okay, we have choose 2 points that we want to use to apply the energy equation. So now we write down the energy equation for that. HA okay, I need to save more space for this problem, so my writing will be slightly smaller. HA plus PA divided by plus VA G equal to HC plus PC plus VC to the earth and plus the head loss. Okay, this is the equation that we want to use, right? And this PA divided by the specific weight is actually P naught divided by the specific weight, which is the parameter that we try to solve. Okay, so what else can we simplify from this equation? For this equation, VA, because it's an open surface, so this term is equal to 0. Correct? Okay, and I think that is the only term that we can simplify. So the height of this A point is equal to 10 meter. Okay, we know that from the problem that I show here. This is the term that we try to solve. And we also know the height for this C point, which is equal to 9.5 meter. 9.5 meter. Okay. And because we want to ensure, we really assume that these C points will have the lowest pressure in this pipeline. So we want to find the minimum P naught, which we choose a threshold for this C point. That means we want to make sure the pressure is positive, so we choose this PC equal to 0. So this term is 0. Okay, that is the minimum pressure that we can have at this point. And we don't know the velocity, so we need to keep this term. How about the halos? The halos here is equal to the friction loss plus the minor halos, right? Which we can further write it down as FL divided by D plus K. Well, how many minor loads that we need to consider for this problem? That's C. First, we have this entrance. Let me use different color. So we have this entrance halos, KE equal to 0.5, right? And we have this valve, the lift type valve, that's KV equal to 12. And the question also tells us that we ignore the band losses for this pipe. So all those bands don't have any head loss. Okay, it seems like before this point we only need to consider KE and KV. So we just write down those terms plus 12 here. 4. And this is velocity term. Okay. And in this equation, we know L, because you can use these things to calculate the length to the C, which is 10 plus the distance here, which is equal to 5m. 7 minus 2 is 5, and plus 5, and plus 7.5 meter for this distance. And then you also know this distance is equal to 5 meter. So you will know the L. And you also know the diameter for this pipe, which is 4 inch. So the term that we don't know yet is this vector F and the velocity C. But for now, we only have one equation here, so we cannot solve two unknown. Let's assume. So what we can do is that we assume the vector F is equal to 0.02, because for the flow inside this pipe is not likely to be a turbulence. So we first assume that the vector is this number, and then we verify whether this number is correct or not. If not, then we correct it. Okay, but now we assume this part. So let's plug this term into this equation and use F equal to 0.02 and just reorganize the equation, and we will find out that the entire this section can be simplified into P naught divided by the specific weight of water equal to 19.9 times the velocity term minus 0.5. Okay. and we call this equation 1. Okay? And as I already said, that we have 2 unknown here. That means we need 2 equations to solve 2 unknown. So let's choose the other 2 points to apply to the energy equation. And this time, let's choose point A and point B. And similarly, we can write down the energy equation like this. Oh, all those V will equal to Vc because the velocity inside this pipe is a constant. Okay, so yeah. So yeah, let me erase this to reduce some confusion. Okay. Where am I? Okay, sorry, I write HB, right? Plus PB plus VB plus the head loss. Okay, this is the energy equation that we'll use for the A point and B points. Actually, you can apply to any points in this pipeline, but choosing these 2, we can simplify more term in this energy equation. So as we have already know that HA is equal to 10 meter, and this is the term that we try to solve. It's P naught divided by gamma. And the velocity term, we don't know. We don't know the velocity. Actually, we know. Velocity for these 2 reservoirs is equal to 0, as I just said. So we can cancel these 2 terms out. And we know that HB is equal to 7.5 meter. And the pressure out here, because it is an open surface, so we can cancel this out. So we remain the head loss for the B point. And the head loss for this B, from here to B, equal to HF, the friction loss, plus the minor head loss. Okay. And is also equal to plus 0.5 plus 12. 0.5 is the entrance head loss, and 12 is this leaf type valve. And what is a global valve? Global valve. Global valve, we have the coefficient this color. Let's use kg equal to 10. So we have 10 here with the velocity term. Okay. And because we already assumed that F equal to 0.02, so and you also know this L to here, you can just calculate using this information that I show on this figure. So I just skip that step, but you can do that using all the information that is here. Okay, so what we don't, F is equal to 0.02, right? So the only term that we don't know is the velocity, right? And the velocity, yeah. So for this head loss, for this head loss, we don't know velocity, so we keep that term and we plug the head loss into this balance equation, and the only 2 unknown will be this P naught and the velocity in the head loss. Okay, so similarly, we can do the same thing to reorganize this equation, which we can got P naught divided by the specific weight will equal to 31.3 times the velocity term minus 2.5. And we call this equation 2. Okay, so now we have the two equations with two unknowns. So we can solve for P naught and the V as well. So change to let me change to different color. We use the equation 1 and equation 2 to got the P naught to got the velocity term, because the right hand side of this equation 1 will equal to the right hand side of equation 2, and the only unknown is V. So we can solve V equal to 1.86 meter per second. Okay, now because we made our assumption here to find out this f, the vector f, right? Now we got the velocity. We need to do backward to verify that our assumption is valid. And how to do that? We will need to use a Moody diagram to find out the vector f using the velocity that we solved using equation 1 and equation 2. So the Moody diagram, to use the Moody diagram, we need this term and the Reynolds number. Okay, and the problem tells us that this roughness, relative roughness E is equal to 0.045, and the diameter of this pipe is equal to 4 inch, and this 4 inch okay. Four inch is equal to 102 millimeter. Okay, so now you have this term, and the Reynolds number is dV divided by the dynamic viscosity, and we know that the diameter is equal to 0.102 meter times the velocity 1.86 divided by the viscosity 1 times 10 to the power 6, and we will have this Reynolds number equal to 1.9 times 10 to the power 5. Okay, so by using the Moody diagram, we will find out the F plane equal to 0.0185. Okay, so it's actually different from our assumption. So in the next round, we use this F plane to calculate equation 1 and equation 2. Okay, then you will get a new V, which I called it, okay, it's 2. You cannot say this, right? Let me write down to somewhere else and use different color. So F plane equal to 0.0185. Okay. So you use this F plane, plug in equation 1 and equation 2, and you can solve a new velocity V plane, which is equal to 1.86. Okay, it's okay. That's a little bit weird. I don't know why this new velocity is equal to the old velocity, but I will check it out and put the correction in the comment area. So go to comment to see the correction. Okay, so let's continue. If we assume that's the new velocity that we found using this new factor that we found by the Moody diagram, we will the new velocity is equal to 1.86, and again we can use this new velocity to check with the Moody diagram and to verify that this vector A plan is correct, is valid. Then we have the velocity term, and we can plug this velocity term in either the equation 1 or equation 2 to solve this P naught. Okay, because this will be the only item that we still don't know yet. So let's use equation 1. Then we will have P naught divided by the specific weight equal to 19.4 times 1.86 squared divided by 2g minus 0.5, right? Plug in here, and this is no longer 19.9 because we have the new epsilon equal to 0.0185. Okay, so this will be the new coefficient. This is 19.4. So you can use a calculator and we can solve that P naught will equal to 2.92 meter. Okay, and then we do a simple unit conversion. That's divided by 9792 Newton per cubic meter, and that will give us 28.6 kappa. This actually, yeah, it's missing one term. Okay, so that is how to solve this problem. Okay, I know it's kind of a maze right now, so let us quickly review how do we view this problem. The problem asks us to solve the minimum pressure at these points to ensure that the pressure in this entire pipeline is positive. And according to our knowledge, we know that the location at the highest location will have the lowest pressure. So we have these 2 points, and we choose this C because the energy will be further reduced by the friction in this section. That's why we choose C as our lowest, as our location where we might have the lowest pressure. So we want to solve the P naught and write down the energy balance equation like here, and because here is the lowest pressure point, so we want to find the minimum P naught. Therefore, we choose the critical value for this PC equal to 0, because equal to 0 to ensure any other place can have the positive pressure. Okay, but after we reorganize these balance equation, energy balance equation between the A point and C point, we found, okay, we have two unknown. One is the velocity and one is P naught. And in order to simplify our equation into two unknown, we need to assume this vector F. And after that, we need another equation to solve for two unknown, right? So we choose this A point and B point and write down the energy balance equation, and we reorganize it using our assumed F vector. And then we can write down the second equation. And we use this equation, we can calculate the velocity. And then we use this velocity and the Moody diagram to verify our choice of this vector F. And we found the new vector F is equal to 0.0185. Then we use this new F to plug into the equation and solve for new V. And we found the new V is equal to 1.86, which is similar to our previous case. So we say that, okay, this is correct. We have verified our choice, our assumption about this vector F. Then we simply plug this new velocity into either equation 1 or equation 2. Then we can solve this P naught, which is equal to yeah, I missed this term. P naught equal to 2.92 meter. And then we can do the units conversion and translate this meter into kappa. And by this term that is right down here. Oh, it's too low. You cannot see. So the bottom part of this equation is equal to 9790 N divided by cubic meter. Okay. Yeah, so the unit conversion, then we got this final answer, 28.6 kappa for this P node to ensure the pressure in this pipeline is positive.
Okay, now let's look at the problem 4.3.2. In this problem is a classic 3 reservoir question, and the problem asks us to determine the flow rate in the branch of the pipe system shown in this diagram, and that means we need to find out the Q1 at pipe 1, Q2 at pipe 2, and Q3 at pipe 3. Given the information shown here, we know the water level, the height of the water level in each reservoir, and we also know the length of the pipe and the unit of feet. And we also know the diameter of those pipes. Okay, so how do we calculate the flow rate? To calculate the flow rate inside a pipe, we need to know the velocity. And to solve the velocity inside a pipe, we can use energy equation. So, for example, if we want to solve the velocity in pipe 1, we can write down the equation, energy equation between the reservoir 1 and this junction. So this Hj at the junction location denotes the total energy level at the junction, which can be expanded to this term. Okay, but actually we don't need the detail of each done. We just need the total energy at the junction. And to write down the energy balance equation between the reservoir 1 and the junction, we can further write down like this. The total energy at the junctions plus the head loads inside this pipe will equal to the total energy at the reservoir, which can be written as the water level height, the elevation height for the reservoir, plus the pressure term, plus the velocity term. And here, we know the velocity at the reservoir equal to 0, and it's the open surface, so the pressure term is also equal to 0. Therefore, we know that head loads, which in this situation we only consider the friction head loads equal to friction head loads, will equal to the total energy at the junction minus the total energy at the reservoir, which simply equal to the water level height here in this case. Okay, now we have this relationship. How does it link to the velocity inside the pipe? Because we know this is the friction head loads, so we can further expand these to the head loads equation equal to the factor F times length divided by the diameter d times the velocity term. Okay, so we know L, we know the length of the pipe, and we know the diameter of the pipe. So the only the parameter that we don't know is this F and the velocity, which is the parameter that we try to solve. So in previous homework, we already showed that if you don't know the F and you don't know the velocity, you cannot really use the Moody diagram to solve this factor because you don't know that velocity. So in this case, we usually will assume a value F and to use the equation to calculate the velocity, and then use this new velocity to update this factor by using the Moody diagram. And we do this process iteratively, and finally, eventually, it will converge to a value that we accept the factor F as well as the velocity term. Okay, but there's one thing that we don't know here is the total energy Hj here. So we will, in order to solve this balance system, we will need to assume a value for this Hj. So in this case, we will have the Hj unknown, F unknown, and velocity unknown. And here we have the 3 reservoirs, so we can have 3 different energy equations. Then we should be able to solve that, because 3 unknown with 3 equations. And how do we verify that the system, the flow rate that we calculate, that we identify using these is correct? That means the flow rate that we solved should also satisfy this mass balance equation. The summation of the flow rate should equal to 0. Okay, so we have this mass balance, energy balance equation and the mass balance equation. Okay, so now we can write down the equation and try to solve all these for the reservoir 1, reservoir 2, and reservoir 3. So here, I show the table to a better visualization to you. So on top of the table here is just the information that we got from problem. The surface elevations, the pipe length, the pipe diameter, and the pipe roughness. Okay, and as I said because we don't know, in this equation we have this Hz, the total energy at the junction, but we don't know that. So here we first make the assumption and then we update that when we calculate the flow rate, after we calculate the flow rate. Okay, so how do we make this assumption? How do we gauge the total energy at the junction, this Hz? We know this total energy should have a value between the maximum energy among those reservoirs and the minimum energy among those reservoirs. So in this case, we choose the energy really close to the second one. Okay, and we will have this 0.1 just to make sure that we won't divide a 0 in our calculation. But you can use any value between the maximum total energy of the reservoirs and the minimum total energy of the reservoirs. Okay, so after we have this Hj, then we know the friction head loads. After we know the friction head loads calculated by this, we then can use our iteration process to solve the velocity. Okay, so now we want to do that because we already have the Hz. We first calculate the E divided by the diameter term and use this and use the Moody diagram to make a guess about this factor F for each pipe. And we also know this term, which we will use for friction head loads equation to calculate the velocity. Okay, so now we know this term, and we also know the friction head loads. So the only unknown in this equation is the velocity. So as I show here, we then can calculate the velocity term based on the friction value that we gauge here. Okay, and this the friction head loads is equal to Hz minus H. Okay, after you solve this velocity, we are able to calculate the Reynolds number, because the Reynolds number is equal to Vd divided by the dynamic viscosity. And you have this term and the Reynolds number, so we can use these two information and the Moody diagram to find out the revised factor F. And the alternative is that you can use this equation to solve for this F. Either way is fine, as long as you can use these two information to find out a new factor F. And after you find out the new factor F, we can plug this revised factor F into this equation again, and we will get a new velocity. Then now we can calculate the new Reynolds number and identify the new factor again. And if these two factors are really close to each other, then we say the value has converged, and we accept the velocity that we calculate at here. So after you got the velocity, the flow rate will not be an issue for you, because the flow rate is equal to area times the velocity, and all those pipes are circular pipe, and you already know the diameter information. So this is simply 2 over d over 2 square pi times velocity. So you will got the flow rate that I show here. Okay, now you know the magnitude of the flow rates, and we want to apply to the mass balance equation to make sure the flow rate is valid. And there's two situations. One situation is that the HJ is lower than the total energy for the reservoir 2. That means the reservoir 1, the flow rate direction for the pipe point is flow to the junction, and the water and the reservoir 2 also will flow to the junction. And for the pipeline 3, the water will flow to the reservoir 3. But if this HJ is higher than the total energy at the reservoir 2, the flow direction at the pipe 2 will be opposite. And we need to consider both of the situation, as I show here. If HJ less than the energy at the reservoir 2, that means the reservoir 2, the water at the reservoir 2 will flow to the junction. In this case, Q1 plus Q2 will equal to Q3. On the other hand, if this sign is opposite, then Q1 will equal to Q2 plus Q3. And we examine the flow rate that we calculate here to check whether under any cases that the mass balance equation can be satisfied. But as you can see here, under both conditions, we have negative value in the summation of the flow rate. So that means the total energy head at the junction is too high. So we need to revise it. So we just find the value less than this value and do this entire process again. And if you do this several times, you will find out, and maybe you can plot your solution in a line and try to find the cross section and identify which total energy head at the junction you should use. But here we just take this value as our next round. Okay. Okay, so as I said, if you pick a new total energy head at the junction, then you plug into here again and do this entire process again. So this term remains the same. You get the turbulence factor, and we already know this. And because now you have the new HJ, so you will have a new HF, because this is HJ minus H, right? And now you have the new HJ here. So you know this, and you know the factor, so you can calculate the velocity using the friction head loss equation. And after you got the velocity, you can calculate the Reynolds number and use the Moody diagram to get this revised factor F. And after that, you can plug back to the friction head loss equation again, and you will get this revised velocity. And to check whether this velocity is valid, you will calculate the Reynolds number again and find out the new factor and check whether these two factors are converged to the same value. if they are the same, then we say, okay, these velocity that we calculated are valid. Then we can use this equation to calculate the flow rate. So again, now we obtain the flow rate given the total head loads that we get here. Then we examine whether the mass balance can be satisfied under either of these two conditions. And we found out, okay, under the first condition, where the water will flow from the reservoir to the junction. And we found out under this situation, the summation of Q equal to 0. So that means Q1 plus Q2 equal to Q3 in this case. So now the flow rate that we found satisfies mass balance equation. So that is indeed the situation in the reality. Okay, I mean for this problem, not in the reality. In reality, we need to consider other things. But yeah, for this question, this is correct. So this is our final answer for this question.
Okay, now let's look at the problem 4.3.6. This is a classic 3 reservoir problem, okay, as our previous problem. But now the system setting is different. We want to solve this water surface level at this reservoir 1. So we know all our information. We also know the total. We also know the pressure turn and the height, water level height turn in this junction. So the only unknown is this WS1, which is the height of this water level in reservoir 1. And the pipe, all the pipe in this problem have the relative roughness equal to 0.6 millimeter. So how do we solve that? First, let's calculate the total energy in this system. So let's write down the step. Maybe let me write down here. Okay. This is the energy level. Energy level. Using the information that we have at this junction. So this will equal to the height of the junction, the water height in the junction, plus the pressure turn, plus the velocity turn. Okay, and because this are a stable system right now, so we don't have the velocity turn. And the pressure term here, the problem tells us the pressure equal to 97.9 kappa. So this is 97,900 Newton per cubic meter, and the specific weight will equal to 9790 Newton per cubic meter. And the height of this junction is equal to 2049. Okay, so we got the energy level for this system is equal to this term divided by this term is equal to 10. So 10 plus 2049 is 2059. meter. Okay, so we know that. Then what else do we need? If the system is balanced, then we should have the summation of the Q equal to 0, right? So if this is balanced, we will have this condition to be satisfied. So that is our target. We want to calculate the Q for pipe 1, 2, and 3, and use that information to verify, to calculate this WS1. Okay, so let's start with the reservoir 2, because we know almost all the information to calculate the flow rate in this pipeline. Okay, so similarly, we write down the energy balance equation for this point 2, and we use and with this junction. So H2 plus P2 divided by gamma plus V2 equal to plus HL. Okay, and we know this term is 2059, which we just calculate here is the energy level at the junction. And for the HL, let me simplify this term first. So because this is an open reservoir, so we don't have the pressure term, and also we don't have the velocity term the reservoir 2. So simply we only need to consider this H2. The H2 is equal to water level from the data, which is equal to 2090. Okay, so the only thing that we need to calculate is this head loss. The head loss is equal to the factor F times the distance of the pipeline divided by the diameter times the velocity term. Okay. And again, we have two unknown here. We don't know the factor F, and we don't know the velocity V. So how can we do that? We need to, when we encounter such a situation, especially for the factor F, we usually just assume a value for factor F. So now we assume that factor F equal to 0.022. And then we can plug these to the water head loss, and we ignore all the minor losses, so we only consider the friction head loss. And this will be times the distance is 1,200 divided by 0.4 meter. 0.4 meter in times the velocity term. Okay, so you plug this water head loss into this equation, then you can solve the V will equal to 3.04. This is V2. 0.04 meter per second. And now, as we did in previous problem, because this f is our assumption, and we calculate this velocity, so we need to use this velocity to verify our choice of this vector f using Moody diagram. So we can calculate the new vector f using the Moody diagram with these two information. E is E is equal to 0.6 millimeter. Yeah, I wrote here 0.6 millimeter. And we also know the diameter is 400 millimeter. And the random number have the formula using this. And then you can find out the new factor and you compare these two. If this one is different, then you plug this new f into the water halos equation and plug into this energy balance equation. Then you compute the new velocity. And you do several iterations, then you can find out what's the true value for, I mean not the true value, but the acceptable approximation for this vector f and the velocity. And here, I can just tell you, okay, our assumption is correct in our case, so it's close enough. So these velocity level calculates are acceptable in our problem. Okay, so I skip the verification step and just simply use this V2 that we calculate using our first assumption. So we can calculate the Q2 using this equation. Then we have times the area of this pipeline is equal to this part. And we know you plug this D 0.4 into this equation, then you can calculate the flow rate that is equal to 0.382 cubic meter per second. Okay, so now we obtain the Q2 here. Okay, then let's calculate the Q3 for this part. And let me change to a different color. So let's calculate. Similarly, we can write down the same thing. H3 plus P3 V3 equal to H8. Let me just skip this writing here, this tedious. We know that the energy level for this term is 2059, and we just need to plus this water halos. And similarly, because this is an open reservoir, so we can, the P3 is equal to 0 and the V3 is equal to 0, so we can simplify the equation to this, which is H3 will equal to 2059 plus the head loads, and head loads we only consider the friction head loads, so we encounter the same situation. Same situation here. We know the length is equal to 2400, diameter is equal to 0.5 meter, and we want to solve this vector f and velocity 3. And similarly, we can assume that vector f is equal to 0.021. Plug into equation, plug in back to this energy balance equation, then we can solve V3 equal to 2.76 meters per second. And similarly, we need to use the Moody diagram to verify our guess of this vector here. And again, our guess is correct, so I skip the verification step here. But when you do the homework or when you do the quiz, you should verify your guess is correct. Otherwise, I cannot give you the point. Okay, so now we have the velocity free here. Use the same equation. We can calculate the flow rates for this Q3. Okay, it's equal to V3 times A3. That's equal to 2.76 times D3. This is 3, 2, and this is 1. D3 divided by 2 square times pi. That is the area of the pipeline. And you just plug in the value that's right on the problem here. Then we can get Q3 is equal to 0.542 cubic meter per second. Okay, so we know this Q2 equal to 0.382. Q3 is equal to 0.542. And now we can use this equation to solve for the Q1, right? But how the water flow here? The question tells us the highest, the reservoir 1 is the highest reservoir, so the flow must be this direction, right? And this reservoir 2 is higher than the reservoir 3, so the flow rate 2 is this direction and flow down to here. So we know that we can expand this equation, and we know that the Q1 plus Q2 will equal to Q3. Why? Because Q1 and Q2 is flow into this junction. So the inflow of this junction should equal to the outflow of this junction, which is Q3. So that's why we have this equation. And by using these, we can easily plug these two numbers into here, and you can solve the Q1. Q1 is equal to 0.16 meters cubic meter per second. Okay. And now we know the flow rates for this Q3. We can further calculate. Oh, that's too low for you guys. Let me. Oh, wrong. This is Q1. Okay. Let me erase this part so I can do the rest of the calculation. Okay, so we know Q1, and then we know the D1, so we can calculate V1. which is Q1 divided by A1. And I skip the step. It's basically the same equation as this here, but with different diameter value. And diameter value that we use for this equation will be 0.3. Okay, so you just do a calculation, then you will get V1 is equal to 2.26 meter per second. Then we can similarly, we can use the energy balance equation for the reservoir 1 and the junction. So I skip as we show here already, because this is a reservoir and it's open surface, P is equal to 0, V is equal to 0. So I can just write down that H1 plus 0 will equal to the energy level that we calculate here for the junction is 2059 plus the head loss. The head loss for this part of the pipeline. And the head loss equal to the factor F times L divided by D, V1 squared divided by 2G. And we know L equal to 1900, D equal to 0.3. We know V1 is 2.26, and we know G is equal to 9.81. And this time, we don't need to guess for this factor F because we already know the velocity. So use the velocity, we can calculate the Reynolds number. That's equal to d times v, the diameter times the velocity divided by the dynamic viscosity. And we already also know this term. E is equal to 0.6 millimeter. D is equal to 0.3, so it's 300 millimeter. Then you use these two information, and by using Moody Diagram, we can find the F equal to 0.0235. Okay. Now, you plug this factor into this term, you can calculate the head loss. And then you plug the head loss into this energy balance equation. Then you can solve for H1. So the final result is that we calculate the H1 is equal to 2097.7 meter. Okay. So let's just do the final review about this problem. So we have these three reservoir setup, but we don't know the water level for the reservoir 1, and we want to use the old information that we provide in this figure, in this diagram here, to solve for the water level for reservoir 1. So to do that, we first calculate the energy level of the junction, because this is the total energy inside this three reservoir system. Then we want to utilize this equation, this mass balance equation, to solve the water level for reservoir 1. And as we see here, we expand this mass balance equation into here, which Q1 plus Q2 will equal, my bad, Q1 plus Q2 will equal to Q3. Okay, so we want to solve Q2 and Q3. And how do we solve Q2 and Q3? The most important thing is that we need to know the velocity inside this pipeline, because the problem already gave us the diameter of this pipeline, so we know the area of the cross-section area of this pipeline. So if we know the velocity inside this tube pipe, then we can calculate the flow rate. And then if we know the Q2 and Q3 flow rate, we can calculate the Q1. And if we know the Q1, we know the velocity inside this pipeline. So if we know the velocity inside this pipeline, we can further use the energy balance equation to calculate the height of this the water level of the reservoir 1 inside the reservoir 1. So that's back to our original. So let's back to solving Q2 and Q3. We can use the energy balance equation as I write down here, and we already know the energy level for the junction, which is equal to 2059. But to balance these 2 points, we have an additional term, which is the head loss, and this head loss is contributed by the friction head loss. And in the friction head loss equation, we found we need the factor F, and we also don't know this velocity. So when we encounter this situation, we always assume a value factor for the factor F first. Then we use that assumed factor to solve the velocity. And then we use this velocity to calculate the Reynolds number and use the Moody diagram to verify our assumption this F factor is correct. If they are deviate with each other, then we use the new factor to calculate the new velocity, and then use the new velocity to calculate the Reynolds number and use the Moody diagram to verify the second choice of the factor. And with few iteration, the number should converge to an acceptable value, and then you will use that acceptable value as our final choice, as our final factor to calculate the velocity. And as soon as you get the velocity, you use this equation to calculate the flow rate, and you go through the same process for the reservoir 3, then you will get this flow rate Q3 at this point. So as I said, you know the Q2, Q3, then you know Q1. You know Q1, then you know the velocity in this pipeline for the reservoir 1. And then you just use the energy equation between the reservoir 1 and this junction to solve the height, the water level in this reservoir 1, as I show the process here, because now the velocity is a known parameter, so we don't need to guess this factor F. You use a Moody diagram to solve to find out what is the number for this factor F. Then you know the head loss. Then if you know the head loss, you just plug into this energy balance equation, then you will get this H1, the final answer, which is 2095.7 meter.